So let's do a little bit of this. I think last week we stopped at the auto cycle, and then we're about to do the diesel cycle. So I'm just gonna go through some of those slides quickly until I get to that point. The topic of this chapter 9 is different than the topic, well, it's similar to the topic of chapter 8 in the sense that both of these cycles are power cycles, meaning we're creating power out of them, except that in 8 we're creating power from water vapor, now we're creating it from gases, right, combustion gases. As I indicated before, this chapter is kind of fairly long. In fact, we only covered these 2 sections last week, so we got a long way to go. So we'll do internal combustion engines, then we'll do gas power plants, gas turbine power plants, and then from there we'll go on to some compressible flow preliminaries. Internal combustion engines, what we're concentrating on is really what happens in a cylinder, right, a car cylinder essentially, in a 4-stroke engine, right, composed of the intake, compression, power stroke, and then exhaust, you know, those 4 cycles. I mean, those 4 strokes. And from here, we had some definitions that we had to go through. We said that the principal ones are the spark ignition or the compression ignition, meaning it's the Otto cycle or the diesel cycle, you know, in plain terms. We talked about some definitions between spark and ignition and compression ignition, but most importantly, we talked about the anatomy of a piston cylinder engine, with the piston, the cylinder, the crank, and the rotary, the reciprocating motion that gets transformed into a rotating motion. Talked about the top dead center, bottom dead center, etc., and some definitions about what the displacement volume is, what the compression ratio is, which is simply the ratio of the max volume divided by the minimum volume. And then we talked about really the actual PV diagram of a cycle, such a cycle, which looks really complicated. And then from there we said, okay, because the pressure goes all over the map, right? How can we talk about a pressure that can make sense, right? And knowing that pressure is associated with work creation, and pressure times volume change is usually work, and we know that a piston cylinder will have a volume change, right? So why not create something called the mean effective pressure, which is defined as the net work from one cycle divided by the displacement volume. But more important part of this chapter is really the air standard approximation or the air standard analysis. Because again, everything goes all over the place, we have to make approximations to make our analysis of the cycle fairly easy. Namely, the 3 or 4 ones are that even though in the piston cylinder you have every cycle you have a fresh charge of air and fuel, right? Because after the exhaust you have to pull in new ones. We have to assume that the cylinder is actually closed and it's the same fluid that is actually undergoing the cycles. Now, when you make an assumption like that, you have to ignore the combustion, right? The details of the combustion, because the moment you go through one cycle, you cannot combust anymore if you don't get any fresh charge. So we replace the word combustion by just heat addition, right? And the exhaust, we just say it just exhausts at constant volume, right? And then the heat addition is the same thing. So the combustion process is replaced by heat transfer from an external source, and there are no exhaust or intake processes as in the actual engine. So the cycle is completed by constant volume heat transfer process taking place while the piston is at the bottom dead center. And of course, we also assume that everything is reversible. That way we can do the isentropic one, so we can do a clean TS diagram if we needed to. A cold standard analysis is the same thing as the air standard analysis, except that there is one more approximation that you have to do, which is that the specific heats, like the C sub P or C sub V, are in addition constant, in the process. Okay? So we're going through that. A system like this now becomes a two processes. Remember, at the heat addition is occurring at constant what? Constant volume, when the piston is at the top dead center, and then the heat rejection is when the piston is at the bottom dead center, right? And then in between you have isentropic because everything is reversible. When we make these approximations, it is easy for us to draw a nice clean TS diagram, because the isentropic ones are obviously are vertical lines, and then these are constant volume processes. Moving on, and this is, by the way, this ideal one with the it is called an auto cycle. And then we also went through this. Once you find what the auto cycle is, in the vapor power cycles, we had 4 points that we needed to calculate the enthalpies on, right? Once you get the 4 enthalpies, you can answer any question you want. And here you have to read the 4 input energies, right? But this one is even easier than what we've done in chapter 8, because it's not like there is a 2-phase or superheated. There is just one table, A22. Once you know the temperature, you can go there and then find what the internal energy is. Once you get all those 4 U's, that's it. You're done with the problem. Now you can find what eta is, the efficiency, and as you go from one process to another, you have to use the relative volume that we talked about last week between one state and another. So between 2 isentropic states, this is what you do. You have the initial VR, you calculate the final VR, and that's what dictates where your final state is going to be. And should you have a cold air standard analysis, you don't even have to do this. You can just find what the temperatures are based upon the relationships here, which correspond to constant CP and CV. Okay, about that. And then we looked at this example in detail last week, right? Again, the whole idea behind a problem like this is to find out what are the 4 U's. Once you find them, you're done, okay? So it's pretty self-explanatory, okay? And that's where we stopped. Now, we're gonna come back and say, hey, let's do the diesel cycle instead of the Otto cycle, okay? So the air standard diesel cycle is an ideal cycle that assumes that the heat addition, the only difference, by the way, is really right here. For the Otto cycle, the heat addition occurred at what constant? At constant what? At constant volume, right? And here we're just saying, hey, we are adding at constant pressure. That's it. That's the main difference, okay? So assumes that the heat addition occurs during a constant pressure processes. Why? Because really the combustion is created by, as soon as you heat to very high pressure, right? Then combustion occurs. So it kind of makes sense to say that it's occurring at constant pressure. That starts with a piston at the top dead center. The diesel cycle consists of 4 internally reversible processes. So on a PV diagram, obviously constant pressure, here isentropic, here constant volume, heat rejection, right? Isentropic. So again, this is the part that is the only difference between the 2. Now, because you have something like this, the work that gets created, right, gets created between 2 and 3. For the other one, for the Otto cycle, we typically add something like this. Right? This is a constant volume, this is a constant volume. I think we went 1, 2, 3, and 4. Okay? And this is where we had the heat addition, you know, Q in, and this is where we had Q out, right? This is P and then V. The big difference between the two, as I said, is right here. Now, during heat addition in here, is there any work done? You think? Is there any heat? Any work done while we are adding heat? Considering that it's heat addition at constant volume.
Delta V.
That's right. If there is no volume change, you're not going to have any work, right? So the only work that happens is really through the expansion in here, right? But how about here? While you are adding heat at constant pressure, is there some work that is being done? Yes, because it is being accompanied by some volume change, right? And you still have some further volume change in here, okay? So that's the only remark that you have to make about this thing. So process 1 and 2 is an isentropic process of the air as the piston moves from the bottom dead center to the top dead center. And then 2 to 3 makes up the first part of the power stroke. In other words, what we are saying here, in the power stroke here for an Otto cycle just goes from 3 to 4, because that's where the volume gets changed, right? But here, you have two parts. You have 2 to 3 in which you have a volume increase, and then 3 to 4 in which you have volume increase, right? So the power stroke is really made up of two phases, if you will, okay? So let's differentiate between 2 to 3 and 3 to 4. Because 2 to 3 is occurring at constant what? At constant pressure, 3 to 4 at constant entropy. So 2 to 3 makes up the first part of the power stroke. 3 to 4, where the isentropic expansion from state 3 to 4 occurs, is the remainder of the power stroke. Of course, 4 to 1 and 1 to 2 becomes essentially the same thing as the Otto cycle, meaning that as in the Otto cycle, the heat is completed by constant volume heat rejection from the air while the piston is at the bottom dead center, and which replaces obviously the exhaust and intake processes of the F4 engine. So again, not much difference between the diesel and the Otto cycle. You still need 4 cases, 4 stuff that you need to do. So this is the Otto, and then if I do the diesel, I'm going to come in like this, like that, like this, and then like that. 1, 2, 3, and 4. So this is P, and this is O. Okay? Now, if you want to find what is the efficiency is obviously going to be equal to the output divided by the input. And what is the output? Well, the output is of a power cycle is always the work created, right? And the input is the heat that you are adding. Where are we adding heat in here? It's between 2 and 3, right? So it's between 2 and 3, right? But why are we saying U, instead of writing U3 minus U2, we are writing H3 minus H2? Because in addition to that, there is a volume change. Remember, H is equal to U plus PV. So when you have something that's associated with a volume change, it's always an H that changes rather than a U, okay? So the equation then becomes, for a diesel cycle, is really to find what U4 is. In other words, here, U. And then you need to find what H2 is. You need to find what H3 is, right? And then U1. As opposed to an Otto cycle in which you need to find really U4, U1, U3, and U2. Okay? These are the only quantities that you need to evaluate for an Otto cycle, right? And for diesel cycle, obviously you need to have these values because that's how you would calculate the efficiency. And as for the Otto cycle, the thermal efficiency of the diesel increases with the increasing compression ratio. This is just like an FYI, right? But this volume, by the way, the volume V3 over V2 has a special name in diesel analysis, and it's called the cutoff ratio. So if you read the problem in which they mention cutoff ratio, that means it's this volume divided by that volume, because you know what is this volume divided by that volume called, right? What is the ratio of this volume to this volume? Talk about that in it's the compression ratio, R, right? So this is the cutoff ratio, and then the compression ratio is either V1 divided by V2 or V4 divided by V3, either one of these. Okay? All right, so the cutoff ratio, and obviously as the compression ratio increases, the efficiency of the thermal efficiency of a diesel engine increases. So, example number 2 is how do you analyze a diesel cycle? It's the same procedure as we have done for the Otto cycle, almost identical, right? And it's, for example, given in this particular, and you have to study these 2 examples, by the way, example 1, example 2. That's what's going to be in the second example. At the beginning of the compression process of an air standard diesel cycle operating with a compression ratio of 18. So when they give you compression ratio, you know what that means, right? It's this volume divided by that volume. And the temperature is 300 and the pressure is 0.1. The cutoff ratio is 2. When they tell you cutoff ratio, that means they are telling you what is this volume divided by that volume. And then you're asked to find what is the temperature and pressure at each one of these points. And then what is the thermal efficiency and what is the Mech, or the mean effective pressure. Those are typically the only questions that are asked for a diesel cycle. So how do you do this? Obviously you need to draw a PV and TS diagram. Always a good idea to do those. For a diesel cycle, for an Otto cycle, this 2 to 3 goes up like this because it's constant volume, then you drop down. For a diesel cycle, it just goes horizontal. So the procedure for analysis is really the same thing, because now you come in, state 1 is already given, the pressure at state 1 is already given as 0.1 megapascals, and the temperature is given. Now, you probably can guess that if the temperature is given, you can immediately find what is the what is the value of U1 from table 22. It's just a direct read, okay? But because T1, because state number, now you know the temperature at T1, you know U1, right? So you need to jump to, and you know the pressure, you need 3 quantities, right? So before going to 2, because 1 to 2 is isentropic, what do we need to do? Remember that famous VR, right? So when you go to that table A22, for that first case, you need to read what is VR1, okay? And then VR2 over VR1 is equal to V2 over V1, which is already known, right? So you can find what VR2 is, and this is what dictates what is the final state. Then you look at that table and try to find what is the state that's going to give me a VR2 equals to 3451. In most cases, you have to do a little interpolation, right? And as you do that, you will find that, hey, it gives you immediately what the temperature is, and in this case, it's not U2 that I want, but I want H2. So you just read the column over, right? So you read T2 and H2, right? Now to figure out what is the pressure, remember the key thing is it's an ideal gas. PV over T is equal to a constant. Okay? So P1, V1, T1 equals P2, V2, T2. So you can find what is the pressure here, and you're done. See? Just by these two steps, you already figured out what is this guy and what is that guy. Okay? Then you want to move up to state number 3. State number 3, which is right here. State number 3 is right there. So since process 2-3 occurs at constant pressure, so 2-3 is constant pressure, that means you don't have to do much for pressure at 3. It's just equal to the pressure at 2. Okay? Now we've got two more things. We've got the temperature and H, right, at this station. So what are we going to do? Well, PV over T is equal to a constant, but P is constant. So that means that PV over T, that means V over T is constant between the two states, right? So V over T is constant. You know V over T for this state, so you can find what is the temperature T3 immediately. Okay? And then finding out what is the cutoff ratio. The cutoff ratio is V3 divided by V2, right? Which again, according to this, it's just T3, T2 divided by T3, or T3 divided by T2, and you find what the temperature is. So it's again marching from one to the other, and the last part is really just another isentropic stuff, which is done essentially the same thing as you've done between the other one. So we go between 3 and 4. I mean, this is isentropic, that's isentropic. So you do the same thing as the VR, right? Same methodology, same ideal equation of state. Now you have read that last value, which is U4 from table A22. Now up to this point, you got all the properties, you got all the states defined, all the temperatures, the pressures, the U's and the H's where need be. Now you're ready to plug in the equation to find what is the efficiency, which is immediate, and what is the MAP. The MAP is simply the work divided by the change in the volume, and then you find that it is equal to 617 like that. And obviously you need to find what V1 is, and it's an ideal gas, so you can just use the ideal gas equation. And then from there you say, well, the average pressure really is about 0.76 megapascals. Okay, so it cannot be as, it may sound like it's very easy to go through this, and I hope that's what you do when you review the stuff, is that you take that problem and then just try to do it independently, you know, step by step, right? And if you reproduce it once, you will be able to reproduce it no matter what the change of variables are going to be. You know, the only difference between these problems is maybe the pressure is not going to be the same or something like that, but the procedure is identical. Okay, so that's the diesel cycle. This one I'm only going to say something about it, but we're not even going to look at the example. But let me tell you why that is what we call a dual cycle. If you remember that pressure diagram that we talked about kind of in the beginning, you see what the pressure happened, right? You know, like this. Do you remember that kind of that weird pressure looking? So this one, you cannot say that it is a constant volume, and you cannot say that it is a constant pressure. So in reality, to be truly representative of a true diesel cycle, it's really a hybrid between the two. In other words, it's a little bit of the what? Of the auto and a little bit of the diesel. Okay? So you're doing the, this part here, it says the pressure volume diagrams of an actual IC engine, which is the one I'm referring to here, are not described well by the auto or the diesel cycles. I mean, both of them are idealizations, but they don't do justice to a true diesel cycle. So an air standard cycle that can be made to approximate the pressure variations more closely is the air standard dual cycles, okay? Dual cycle, you can probably see that here everything is the same, The only difference is that we are breaking up this part for heat addition into maybe one part that is at constant volume and one part, it's like I have a foot here and a foot there, right? So what's the downside about this versus what we've done before? The analysis is going to be identical, except that we have how many states now? 5 states instead of 4, okay? So it's just one additional state that you have to worry about. So I'm gonna skip this part. I figure if you know the exact Otto cycle and diesel cycle, you would know the dual cycle. Right? Okay, just a few words about, at least to get us going with the gas turbine power plants. I mean, so far we've been talking just about a gas that is confined in a gas cylinder engine, right? But this one is a bit different. If you have, for example, I mean, it's still a power, still a power cycle. Gas turbines tend to be lighter and more compact than vapor power plants studied in Chapter 8. Chapter 8, we had those 4 components, you know, which are 2 heat exchangers, a turbine, and a pump, right? But these ones tend to be lighter. Why? Because the density of water is pretty darn high, right? Compared to something that has air, which is much lighter, right? So you cannot take a vapor power, you cannot take a water thing, you know, and move it from one place to another. It has to be kind of stationary. The favorable power output to weight ratio of gas turbines makes them well suited for transportation applications. Now you can put them in things that actually move, right? Like aircraft propulsion, marine power plants, and so on. Gas turbines are also commonly used for stationary power plants. I mean, it's not just for things that move, but you can also use them for stationary power plants. Now, what is the big difference between that and what we talked about before? If you look here, this is a schematic of a simple gas turbine. A simple gas turbine will have this. You remember, for vapor power plants, we are compressing the water. We are pumping it to raise it to a higher pressure. When you talk about compressible fluid, we don't talk about pumping, but you talk about compressing, okay? So you have to have some air that you are pulling from somewhere, right? And you are compressing it, right? Then what happened to the vapor power plant? After we got that, we take it to the boiler, right? In which heat gets transferred there, right? In this case, we bring it to a combustion chamber in which the combustion occurs, right? And then after that, just like in the vapor power plant, after the combustion, where do we go? We go to a turbine. That's where we generate the work, right? What is the difference in here? In the vapor power plant, we go from here to where? To a condenser, right? And then from the condenser, we pump, because we need to remove the extra heat, and then turn the 2-phase solution into just liquid solution, right? Which we pump again and then come back up in here. Here we're pulling this from atmospheric air. And then we're compressing it, right? We are causing the combustion, and then the combustible air, you know, are run through the turbine, and I'm getting a shaft that's turning. So I'm getting my work. And then after the turbine, where do the products go? They're just expanded out, right? Then, of course, in reality, you go, okay, that's fine, but from a thermodynamics point of view, it's a problem, because we know how to analyze cycles, right? But if things go like this, there's a break in here, you know? How can I figure out how can I analyze it with what I have learned for cycles before? So we'll have to make some approximations. We're going to say that, hey, we're compressing something, right? And then instead of talking about combustion, again, we ignore combustion. What do we say? We're just adding heat. Okay? That's the same thing, right? That's the goal of the combustion. And then after you go to the turbine, what is the difference between these two? I mean, granted that obviously this is, you need fresh air, right? Through oxygen and this and that, so you can do the combustion. But in reality, really the big difference between the two is that this fluid is hot and this fluid is cold. So what approximation can you make? You're going to say, well, I can close this loop in here by assuming there is a heat exchanger that takes these products in here and remove that extra heat and bring them to the temperature of the inlet. That's a fair approximation, but I feel much comfortable with this than I do feel with this, because now I can recognize this as being a true power cycle, because I have a heat in, I have power that gets generated, and I also lose some heat because, remember, to satisfy the second law of thermodynamics, right? But what else is different between this and vapor power cycles? Do you see the shaft that's going right here? Why is it going all the way through? You think? Because the compressor needs power, right? Where the heck are you going to get the power from? I mean, this damn thing is moving up this and that. So maybe we should use part of the turbine power to run the compressor, because now it's a compressible fluid, right? That means it's going to need a lot of power, right? So the compressor is going to eat up a lot of your turbine work, as opposed to the pump. You know, you're pumping something that is incompressible, it's not much, but here it's pretty substantial. So you have a shaft that is typically linked between the two to run the compressor. So let's read what's going on there. It says atmospheric air here is continuously, this is on the open to the atmosphere one, atmospheric air is continuously drawn into the compressor and compressed. Air then enters the combustion chamber where it is mixed with fuel and combustion occurs. The combustion products expand through the turbine and are discharged to just the surrounding. Okay, that's the normal stuff. But here, this is the closed one. The working fluid receives energy input by heat transfer from an external source. The gas exiting the turbine is passed through the heat exchanger where it is cooled to prior to re-entering the compressor. So, okay, some idealizations again. An idealization is often used in the study of open gas power standard, which is the same thing as air standard analysis. Okay, this is very famous. The two assumptions is that the working fluid is air. So we're not going to talk about different compositions or something like that. So by closing the system, we're assuming it's the same air that is turning around in the cycle, right? It's just being heated and cooled and heated and cooled, etc. And it behaves like an ideal gas. Why is this important for us, you think? Because we can use the ideal gas equation if we need to calculate something. And the temperature rise that would be brought about by the combustion is accomplished by heat transfer from an external source. Again, just like for the combustion cycle, right? We're not going to say it's combustion, but we're just going to call it some heat addition from an external source. Now, with an air standard analysis, we avoid dealing, obviously, with the complexities of combustion and the change in composition. And it analyzes, and it obviously simplifies the analysis of the turbines pretty well. Okay, moving on now to the third cycle that you're going to be learning in this chapter. Third and hopefully the last one. Well, there's going to be another one for refrigeration down the road, but the Brayton cycle. Okay, so we talked about Otto cycle, we talked about diesel cycle. That's for combustion, right? In other words, for air that is confined. And here it is something that's going through 4 units. This is almost like the vapor power cycle. So what do we have? We have air would be drawn into the compressor at state number 1. So compressor is always state number 1. from the surrounding and then later returned to the atmosphere at state 4 with a temperature greater than the ambient temperature. So after interacting with the surrounding here, each unit mass of discharged air would eventually return to the same state as the air entering the compressor. So you could think that, you know, even though this is kind of a new air that's being brought up in here, you could assume that it is this guy that actually continued on after losing some of that heat. So we may think of the air passing through the components of the gas turbine as undergoing a thermodynamic cycle. Because when we do this, then obviously how many values, what are the values we need to do to analyze the cycle? The H values, just like the vapor power stuff. In fact, it's even easier because everything is temperature dependent. You don't need to dance around with many tables, okay? So if you need H1, H2, H3, H4, let's look at the compressor, for example. Do you think the H at 2 is higher than H at 1?
Yes.
Yeah, because you're compressing, you know, you're raising. So what is the difference between the H's, you think? It's more likely the work that the compressor is using up. Okay? How about here? Is H3 greater than H2? Heck yes, because we're adding heat. Whatever is going to come out is going to have a higher enthalpy than the heat in. And the difference in H's, just by looking at this, you know there is no work. This is like a little open system, right? The only thing that's going through the boundary is Q, right? So H3 minus H2 is equal to simply Q in. And then looking at this guy, and then you go like, okay, which one is higher, H3 or H4, you think? It's more likely that it's it's not more likely, it is H3, right? Because that's really what's coming out right after the combustion, before the gas expands, right? So H3 is going to be higher than H4. So how come it lost H3 to H4? What happened in between? Well, the difference is the work that is created by the turbine, which is equal to H3 minus H4. Last but not least, which one is higher? It's obviously when it's warmer, that means H4. And the difference between the two will correlate well with the heat that is lost by the condenser. So it's nothing new. Meaning that once you find what the H's are, what else can we find? We can find what the efficiency is, we can find everything else, right? So that's really what the next slide is, right? The work of the turbine is H3 minus H4. The compressor work is H2 minus H1. Heat added is H3 minus H2. Heat rejected is H4 minus H1. So for you to analyze a Brighton cycle, really ends up like finding really 4 H values for those 4 states. Once you find those 4, done. Just like the vapor power cycle that you're going to be doing today, you know. Once you find the correct 4 H's, then the rest is really just plug and chug, as they say. Okay, so now that you have all these quantities, finding what the efficiency is no big deal, right? What is this? This is called the net work, right? Because the turbine produces, the compressor uses up work, right? So you have to subtract the 2 and divide it by heat in and whatever. And look at this again. This comes back up again. Back work ratio. Remember what back work ratio is for the vapor power cycle? It's the work of the turbine. No, it's what?
The pump divided by turbine.
Oh, pump divided by turbine. Thanks. Yeah, that's exactly right. And here, instead of pump, it's the compressor. Compressor divided by the turbine. Do you think the back work ratio for a gas power cycle is going to be higher or lower than the vapor power cycle? And why? Well, hint. In the vapor power cycle, you're dealing with water, which is incompressible, very hard to change the volume of water, right? So the work done is not going to be that as much, right? Whereas here, you're dealing with a gas. As you change the pressure, the volume change is going to be pretty significant, right? So the back work ratio for a gas power cycle is going to be much more important, much more significant. That's why we had to reroute some of the power that is produced by the turbine to just run the compressor. Okay, so the compressor is going to eat up a significant amount of the power. In fact, I have some numbers here. It says for the same pressure rise, the gas turbine compressor would require a much greater work input per unit mass flow than the pump of a vapor power plant, because the average specific volume of a gas flowing through the compressor would be many times greater than that of the liquid passing through. Okay, this average specific volume. You see, water versus vapor. Vapor is going to have a larger specific volume, volume per unit mass. Hence, a relatively large portion of the work developed by the turbine is required to drive the compressor. Typical back work ratios of gas turbines range from 40 to 80%. I mean, the work on the compressor could be between 40 and 80%, when you of the turbine work. Okay. In comparison, the back work ratios of vapor power plants usually are about 1 to 2%. So that's what it is. I mean, you get high power to weight ratio, but you lose a lot of things. All right. So ideal Brighton cycle. Ideal Brighton cycle using available air data, because now we have two processes that are at constant pressures. See, anytime you have, by the way, just so you remember, anytime you have heat exchangers, the process that goes through the heat exchanger is always a constant what process, you think? It's a constant pressure, just like the vapor power cycle. What is the assumption that we were making there? It's a tube that carries fluid, right? What we are assuming is that there is no friction between the fluid and the walls of the tube, okay? That means we are not losing pressure, and therefore it is a constant pressure process, okay? So here, it's going to be an isentropic process because we are assuming these two things are reversible, and then here, it's going to be a constant pressure processes, right? So, when you do that, then obviously you have two constant pressure processes and then two isentropic processes. And how do you go from one state to the other? Before we had, for the combustion cycles, we had constant volumes here in the isentropic ones, or at least between the isentropic ones we had constant volumes, right? Here we have constant pressure, right? So instead of using the relative volume, the V sub r's, we will be using the P sub r's. That's all there is to it, That's why the ratios of the PRs is going to be equal to the pressure ratios, because a compressor is not going to have a compression ratio. It's going to have a pressure ratio or compression ratio, which is the high pressure versus the low pressure, right? So this is using the available air data, this is the stuff that we're going to be using. And then when we do the cold air standard analysis, if the CPs are constant, then that is the procedure we will be using. So let's just take a look at this one and then we'll end it here. So again, how do we analyze an ideal Brighton cycle? Well, you have to draw, unfortunately for here, not unfortunately, but fortunately, we did, for the combustion cycle, we did not draw the physical thing. Why? Because it's just a cylinder that's got fluid in it, big deal, it's not like it's state 1, 2, 3, 4. Here you got 4 components. You got a compressor, 2 heat exchangers, and a turbine. With state 1 is the entrance to the compressor, right? And remember, for vapor power cycle, state 1 is the entrance to the turbine, okay? So always kind of think about this as like the opposite one, right? And always you go in a clockwise direction. So air enters the compressor at 100 kilopascals. 100 kilopascals at state 1, and temperature T1 is given, right? with a volumetric flow rate of 0.05. The compressor pressure ratio, instead of the volume ratio, it's the pressure ratio is 10. That's why we use the PRs instead of the VRs. The turbine inlet temperature is 1400, so this temperature is given, this temperature is given. And then you're asked to find what is the thermal efficiency, what's the back work ratio, and what is the net work output. Again, before you even delve into this, how many properties are we seeking in here? 4 properties, namely H1, H2, H3, H4. Now, looking at this state number 1, do you think H1 is going to be a big deal? No, the temperature is given, right? So I just go to my good old table, right? And then read from there immediately what is the value of at 300 degrees, what is the value of H1, which is simply 300.19. Because it is the start of an isentropic one, I need to read what PR1 is, and then I find PR2 based on the pressure ratio. Now I look in that table, okay, what is the temperature and pressure that corresponds to this? There's only one answer, okay? So in most cases, you'll have to interpolate because it'd be lucky to find fall exactly on the point. But 1386 would correspond to a value of H2 of 579.9. Done, okay? And then you go on to state number 3. State number 3, the temperature is given. So again, life is easy there. There's no equation you have to use. You just read the value of H3, which happens to be 1515.4. And because again, it is the start of a isentropic process, you need the PR3 from which you calculate PR4. Once you get PR4, you just find that state number 4 directly from there. So it's much quicker, in my opinion, than it is for vapor power cycles, which sometimes you are in the superheated, sometimes you are in the inside the dome, sometimes you are on the left-hand side, okay? Once you find those, then no sense even talking about this because the equations are available, and then you just plug those values in there to find all the answers that you are seeking, because everything, after all, is a function of the ages that you have just calculated. Now, the entire rest of this chapter, by the way, is going to be more of an informative thing, at least for this cycle. Which I think we can finish. This is, let's just see what I have in here. And just like for the other one, by the way, I just need to finish this section. I think it's 2 more slides. 962. And as the pressure ratio increases, it goes without saying that you're going to have a bit more efficiency, okay? So this is experimentally how that's been established. Ideal Brayton cycles with different pressure ratios and the same turbine inlet temperatures. What do you see here? 1, 2, 3, 4, 1. This is an isentropic, constant pressure, isentropic, constant pressure. So that's an ideal Brayton cycle. How about 1, 2 prime, 3 prime, 4 prime? That's still another ideal Brayton cycle, right? Because you still have 2 isentropic processes and then 2 constant pressure processes. So what are we talking about in here? Remember, anytime you want to increase the efficiency, what you want to do is you want to increase the temperature of heat addition. The hotter the fluid, the hotter TH is. Remember, for Carnot cycle, 1 minus TC over TH. As TH increases, then you can get better efficiency. So it says here there is a limit of about 1700 K imposed by metallurgical considerations on the maximum allowed temperature at the turbine inlet, because that's where the action happens. You see, whatever goes into the turbine is really what came out just out of the combustion, right? You don't want those temperatures to be too high to interfere with the metallurgical capabilities, I guess, of the turbine components. So it says 1700. It is instructive, therefore, to consider the effect of compressor pressure ratio on thermal efficiency when the turbine inlet temperature is restricted to the maximum allowable temperature. So remember what 1, 2 does? This is the compressor, right? 1 is the entrance to the compressor, right? And then 2 to 3, this is the exit to the compressor. What happens between 2 to 3? Your heat addition, right? Right? So what if, for example, if you want to increase the temperature of heat addition, right? Maybe if this is the maximum temperature, you're going to say maybe my average here between 2 and 3, the temperature of heat addition is probably going to be somewhere here on average, right? But if I compress my fluid, my air a bit more before adding the heat, then my temperature of heat addition now is somewhere there, which is better than somewhere here. So technically, you have a larger thermal efficiency, okay? But it says for cycle A, to develop the same net power as B, a larger mass flow rate would be required. Because after all, what is the temperature, what is the area under the curve represent? The heat, right? You see here, I may get more efficiency, but I'm going to get screwed up in here because my area is not going to be as large. See, I gain one thing, but I'm not going to gain much heat. So if I have, for example, a specific amount of heat that I would have to need, the only way to make up for this reduction is to increase the mass flow rate, you know, just to kind of make up for that, okay? It says cycle A has a higher compression ratio and therefore a high thermal efficiency. So this is a show just to kind of see that, and I'm not even going to deal with this example here. And this is again isentropic efficiencies. I decided not to even get into them into here because some of these processes, obviously 2 to 3 is typically a constant pressure process, right? But in reality, what happens to a fluid as it goes through a pipe? What happens to the pressure? Inevitably decreases somewhat, right? So you see here, instead of going through this pressure line, you know, technically you're going to go to one that is a little bit close but lower, right? And the same thing in here, as you go from 4 to 1, it's again a reduction in pressure. Now, if you ask me, is it more complicated to analyze these two than the ideal ones? Yeah, because you have to include these steps to actually get the values, let's say, of H4 based on H4S, and to get the value of H2 based on H2S by using the isentropic efficiencies. Okay, and this is what this example is just repeating that first one with the isentropic efficiency. And I think I will end here, and this is where we're going to pick it up next time. And I'm hoping that next time we will probably be able maybe to finish chapter 9. I mean, we'll try. Okay. So that concludes.